Okay, finishing up our very last problem, and it's a problem that's been modified from the notes. We have a region that contains a hole. We're between the circles x squared plus y squared equals 1. That's a circle with a radius of 1. We also have x squared plus y squared equals 4. Well, that's a circle centered at the origin, radius of 2. But we are between those two circles, so we could call this an annular region. That's an annulus. And we are going to investigate this line integral right here. We'd like to see if maybe perhaps we could get this worked out. Maybe perhaps as a double integral rather than a line integral. Otherwise, we'd have to look at our curve parametrically. You can see that there are two parts to it. That might not be the best, funnest way to do the problem. But my goodness, if we were to use Green's theorem, real quickly, let's remember what's happening. Up here we have P dx, Q dy. Because we have a positive orientation, we're going to have a double integral, and we're going to have, thank goodness, partial derivative of q with respect to x minus partial derivative of p with respect to y. And we're going to integrate over this region with this double integral. So we're going to have q with respect to x. That is a derivative of just 3y. The derivative of p with respect to y would be 2y. And very quickly, I hope you can see that this double integral could be done considerably more quickly if we did this in polar. And that can happen quite often. Polar is definitely the way to go because y is equal to r sine of theta. So continuing up here, we're going to have r sine of theta, but remember that dA is going to become r dr d theta. And our boundaries for r, well, we're going to be going between 1 and 2. How about for theta? Well, we'd be integrating between 0 and 2 pi. And very quickly we're going to notice that we have r squared and sine of theta. Wonderfully, you might remember from a previous chapter, we could do something very clever. We can actually separate the double integral into two single integrals right now. You might remember that method. This is the integral from 1 to 2 of r squared dr. This is the integral from 0 to 2 pi of the sine of theta d theta. And we could work these two out individually, multiply their answer together. Antiderivative of r squared is r cubed over 3. And we can evaluate that between 2 and 1. Well, plug in a 2, 2 cubed is 8, so we'd get 8/3. Plug in a 1, we'd get 1/3. So this is going to be 7/3. We'll work that out in just a moment. What's the antiderivative of sine? Well, we get negative cosine. And we'll evaluate that between 2 pi and 0. But look, very quickly we can see that this is negative cosine of 2 pi minus negative cosine of 0. Well, minus a negative, of course, is going to become a positive. But the cosine of 2 pi and the cosine of 0 are both 1. So this would become negative 1, and this is still a positive 1. Wow, this is a 0, and this is 7/3. Our final answer is going to be 0. Please don't misunderstand. I think this is something that we had to talk about in class as well. That this double integral that we have right here is really not reflecting the area of that region. Remember, we're really evaluating double integrals like we did last chapter. It's thought of as a volume, actually. in this setup. And it's perfectly okay for double integrals to equal 0, and for line integrals to equal 0 as well. Remember, line integrals can be positive or negative. So that's where we're wrapping up. Just wanted to let you see how we can integrate over a region with a hole. Okay, so keep working. We're going to be doing a lot of review in the next few days, hopefully pulling a lot of things together. Good luck.